Okay, I think we'll get started. I'm Bryce Clark, I'll be chairing the session. I'm happy to introduce our first speaker at the session who will talk to us about inference diagrams in the category of Markov kernels.
Okay. Hello everybody. So I'm very happy to be here and to give this talk. So it's a bit different from the one this morning. It's related subject but very different in a way. So I will be talking about inference first and spend some time on what inference is. So that we can all talk the same language, and then I will explain how you can extend inference for more general probabilistic models. And so before that, let's try to see what happens in deep learning when you study when you want to look a bit things more compositionally. So deep learning has a big problem, which is called curse of dimensionality, which is basically if you have data that is too high dimensional, it's very difficult to train. And the reason is because there's a problem that the measure is going to, it's very difficult to estimate the volume of a sphere. So the idea is to instead use some invariance in your data to be able to reduce the dimensionality of your data. And if you want to do this, one celebrated example is, for example, if you want to take away translations, you're going to develop an architecture that's able to be equivalent to translations. And these are CNN, convolutional neural networks. And then you can filter out translation on the last layer when you're going to decide to classify. And then there's a more recent way of doing it for other kind of geometric, let's say if you want to encode some kind of geometry on your data, you're going to discretize it. And to account for the geometry of your data, you're going to use graph convolution. We discuss GNN, graph neural networks. But in this setting, what happens is that nodes share same features. And so the space in which the features live on the nodes is the same. And this is a limitation because if you have heterogeneous data, you would like to have that on nodes, you don't have the same feature spaces. So a way to account for heterogeneity is to introduce for each node a feature space, and for each edge, you're gonna put a linear map, and you can also study higher dimensional structures using, for example, cell complexes and adding two faces features and inclusions linear maps. And this is instead of setting up cellular sheaves. And a way to train, so this is a kind of data, basically it's your data input. And a way to learn on these data is to consider what is called a sheaf neural network. Okay, one limitation in this framework is that, at least from what I know, in the higher dimensional objects, not graphs, but higher dimensional, there's a limitation is that you start from something that has a structure like cell complexes, and you don't consider any poset or any hierarchy. And Bayesian modeling is very good in considering hierarchies in general. So the aim of the talk is not to do deep learning, but to do the other thing, which is Bayesian inference. And so Bayesian inference is probably very, very known thing, huh? Even if it's less represented maybe now, at least not on its own. And so in Bayesian inference, you talk about graphical models. So you find a way to describe the dependencies or independencies, conditional independencies between your variables. You can go to higher dependencies like Markov random fields, where you are allowed to have, let's say, dependencies on more than, you describe the dependencies not through couples of variables, but through collections of variables, through Markov property, or through factor graphs, which I will present. And this is one of the first part of my talk will be dedicated to presenting this and the tools to do inference on these objects. And here, you don't have a limitation that you have to be in a simple complex or cellular complex, like cell complex, sorry, but you have a very big limitation, which is you cannot consider heterogeneous descriptions of your variables, which means that if you want to do a graphical model, you need to be able to observe all your variables at the same time, and you cannot say, I'm going to observe these variables, and I'm going to see how they relate. So let's take an example. If you have a camera that's looking in this direction and a camera that's looking in this direction, there's an intersection between both, have partial information, and would be able to say, okay, but I have partial information, but they have some kind of consistency on the intersection. So this is what we're going to try to do today. We're going to try to extend the formalism of Bayesian inference to account for heterogeneity and non-local description of local description of information. Okay, and this was done independently from the work before, which means that it's even if Curry's work is far away, way before. It's my fault. I should have known more about the literature, but I mean, it's a different direction, even if you have similar ideas, but it's not inspired from these ideas. So first graphical models, then factor graphs for generalized the two, then inference. Inference is belief propagation. It's extremely important algorithm. It's what is message passing algorithm, very general class of algorithms for inference on this. Graphical models, okay, sorry. Graphical models, factor graphs, and you want to see them now as contravariant functors to be able to account for heterogeneity. And what is new is so this is basically where the limit appears, how you go from classical setting to more functorial setting, but this was already known in the literature, but not written, not seen in this way. But here it's for a very restricted kind of contravariant functor. And here we go full-blown contravariant functor, like where you're allowed to have much more general maps, stochastic maps, and we'll explain how to do inference on this. So first, a graphical model, it's a graph. For each node, you're going to have a variable. And you're going to say that you have conditions that you can read from the graph that tell you in the conditional independence conditions. So you have several conditions that you can read from the graph. The simplest one being this one, yes, which says that if no, I think this, yeah, okay, this one is the simplest. Sorry, if you take, I mean, it's simplest to understand. If you take a node and you look its neighboring in the graph, you want to say that if you condition on the neighboring, then you're independent on what's not around the neighboring of the node. If you do this, and so both are equivalent if you assume that P is strictly positive, but I didn't say how. You can restrict, this information allows you to restrict the space of distribution you consider. So you read from the graph some conditions and it gives you a factorization on the probability distribution that you consider. So factorization is simply saying that you take P, you take a sub-collections of variables. So you take a collection of finite, so you take a collection of sets, and these sets are collections of finite variables. And so for each one, you have a term which corresponds to, let's say, local distribution, and P is the product of all of these. So we say that we have a factorization model with respect to a poset. If, in a poset being inside P inside of the power set of I, if it can be, the distribution can be factored this way. There exists a collection of FA such that it factors this way. That relates to what we said this morning, which is basically that if you take logarithm, you get energies. And so these are statistical systems, like we said this morning. Now, this is the very strong result from Hammersley-Clifford that tells you that the conditions that you have, that you can read from the graph, are equivalent, in fact, to a factorization of the distribution, and it factors on its clicks. So you say a probability distribution is a graphical model, so satisfies one of the conditions that you can read on the graph, if and only if it factors with respect to the clicks of the graph, which means that every time you have a click, you put a term, FA, that depends on the variables of this click. Okay, and now, so basically, factorization is the most general description that you can do for probabilistic, for all these graphical descriptions or factor graphs. Like really factorization, the way the distribution factors is the most general space of sets for which you can say something in terms of Bayesian inference. So inference, how is it done? It's done through belief propagation, which I will explain after. Okay, so if you look at what are called directed graphical models, I didn't talk about it, but it's called Bayesian networks. In fact, Bayesian networks, you could say, oh, it's very used because you can interpret it and it's cool, but in fact, no. The reason is because a Bayesian network, if you want to do inference, you need to transform it into a tree, into an undirected graphical model. And so in fact, the real thing is undirected graphical models, not directed graphical models. So now, what are factor graphs? Factor graphs are simply trying to account for having more interaction, like not pairwise interaction dependencies between your variable, but higher ones. So you're going to say that every time you consider a collection of variables, A, and though this collection, you're going to associate a node, And then you're going to say, every time the vertices is inside of this collection, I put an arrow. So I have a bipartite graphs for each family of variables that I will consider, and for each variable that is inside of this family, and the edges are defined this way. So the simple example is if you have a graphical model, x, y, z. So this is saying that p of x, y, z is equal to p of x, y times f of x, y times f of y, z. Then the factor graph is simply for each edge, you add a box and you put the factor associated to the edge. And not saying anything new, but this is interesting here because in fact, the inclusion relation in the edge tells you that basically you have a poset. So I mean, just saying what a graph is, if you see it as a poset, and now you're saying that you have a way to go from, and at least graphically, it's not informative, but you say that you go from x inside of the edges, and now to go to x to y, you need to go inside of the edges. And this idea will come very often later. So factor graphs generalize graphical models, and same thing, well generalized as all this are factorization models, statistical mechanics. Because I wanted to give an example of how you can do inference, and basically to do inference, you need to compute marginal distributions, and how you can compute marginal distributions on graphical models. So this is a graphical model, and let's say this is a graph, and I'm going to consider the graphical model underlying it. So we use Hamilton-Clifford theorem. It tells me that it's just the factorizations on things on the edges. And now I want to compute P of A. So I need to sum over. So every time I have an edge, I have a distribution or conditional distribution, okay? PAB, PCB, PDB. And I want to be able to compute P of A. So I need to marginalize on everything except P of A, except A. So if I do it in a recursive manner, so assume that you have summed already on F. So you have a message MF to E, and you want to see what happens after. So you can forget about this node, only consider this graphical model, and then you have the expression that falls this way. And then now you can take, and it doesn't depend on B anymore. I mean, it doesn't, so you have three sums, one on C, one on D, one on B, but you had what came from MF E, if you sum on E, goes on D, and then you can put it on the left, and then you have just a sum on C and sum on D. So you see that you can have a recursive formula between the sum that you want to do on A and the sum that you would like to do on B. And this also depends on the sum on C and the sum on D. So this is called dynamical programming. I mean, I said it in a very dynamic program, dynamical programming, dynamic programming or dynamical programming. Maybe you know, dynamic programming. Sorry. So this is an instance of dynamic programming, and in fact, there's a way to formalize it. Let's say, there's a way to extend it. It's not computationally, okay, there's a way to generalize it, but it's not really a generalization. It's just doing things, not waiting for your messages to finish at some time to update, but just doing it at each node, at each moment. So you're going to put, for each edge, you're going to have two orientations, xi to xj, if you have an edge between I and j, and xj to xi, and you're going to associate a message that goes from I to y, that is in fact a distribution on P of Ej. So I mean, this is the state space of Xj. Now, if you do this, you have the formula that I just gave before, is equivalent to computing this, which means that you're going to wait. At time t, you have messages that are flowing in your graph. And what you're going to do is you're going to put a term associated to your edge, so the energy associated to your edge, exponential minus beta h, times all the messages that come from the neighbors of I that are not j. So this is called, this algorithm is the belief propagation algorithm. Interestingly, it extends, so it allows you to compute the marginals. Once these messages stay the same, this happens in finite time if you're on a acyclic undirected graphical model. Which is what you get when you have DAGs also. So yes, if we say that the algorithm stops when the next messages is proportional to the previous one, and then you have this very nice result which tells you that you computed the marginal distribution. So this is an instance of what is called filtering, smoothest filtering for Gaussian hidden Markov models, which is one of the most used algorithms in engineering. Okay. Now, okay, so I said that we have a dynamic programming algorithm to compute the marginals, and I said this is related to inference. I didn't say why. So because you have a very nice result, this if you have an acyclic graph, the distribution factors this way with respect to the marginal distributions. Okay, di being a degree of the node. So you have on the above, you put the product of all the p. So take the example of this one of the line here, pxy, pyz, marginal distribution. The pxyz equals pxy times pyz. That's not completely correct because you counted twice y. You need to divide by py. So this is exactly what this formula is telling you. You just do the products of the marginal distribution on the edges, but you need to take out the number of times you counted too much the marginal distribution of the node. Now, interestingly, when you want to do inference, or Bayesian inference is simply minimizing a Kullback-Leibler divergence, which is the same thing than maximizing an entropy under a constraint of energy, expectation of energy. So, okay, this is known. You want to do inference on a graphical model, you just need to do this. But in fact, entropy can be broken down into terms that depend only on the marginal distributions. And here you see appear something that's nice, which is the inclusion-exclusion formula. You do not want to count more time. You want to take out the number of times where the intersection of two edges appears, because you don't want to overcount them. So what people what people realize, in fact, is that you can forget about entropy or energy or Gibbs free energy and just consider things that depend on local variables, QA, and introduce this quantity, which is the same as entropy, basically, if you have an acyclic graph, but depending only on the marginals. And now you don't want to solve maximum of S for the graphical model, or minimum of the free energy for the graphical model. You want to solve this quantity under the constraint that your marginal distributions are compatible through marginalization. Okay, so this is much more interesting because now you don't need say you have a functor here that is simply the one defined by the projections from the state space on the edges to the nodes, and you have a marginalization, and then you say, okay, I can in fact define the problem of inference locally with respect to simply putting constraints on how the distributions have to evolve. And in fact, belief propagation is simply a discrete time gradient descent on the Lagrange multiplier of this quantity. So belief propagation, if you know how to define this optimization problem, you get the belief propagation algorithm. And very interestingly, it took time to realize that they both were equivalent. That the dynamic programming algorithm is the same than solving this optimization problem. And this gives you a way, a scheme to solve it. Okay, so moving forward a bit faster, now we can consider any collection of subsets of variables to play the same game. We have projections between state space for a collection of variable that is bigger than the other one, and I say that this is a graphical pre-sheaf. The only thing is that you consider only projections, and you can only have state space which are defined as product of individual state space of variables. So now the new game is to say, I don't want to do this, I want to replace projections by any morphism, in fact, any stochastic kernel, any Markov kernel, any stochastic map. And I want to be able to do inference in the same way by introducing a message passing algorithm. And in fact, it's possible. And this is what I want to present today. So how can it be useful? How can it be useful? It can be useful if you imagine a system of agents that have to collaborate and they have different world models and they can communicate their priors. First system. Second is when you want to have effective potentials, effective energies for in computational chemistry. This can be very useful in this setting, and this is what we're implementing now with some students in the internship. So first one is with Niels Ruer, who is the second author in this paper, who's a PhD student co-advised by David Rudroff, Alain Finkel, and myself. And this one we're working with several students from our masters. Master's beam in computational biology. Okay, so now the idea is your category is a category of Markov kernels over finite measurable sets. Then now your functor is any functor that you can go put inside. And the free energy stays the same, doesn't need to change. Here I just put a discount term for inclusion-exclusions, which is the inclusion-exclusion formula for the coset, which I'll introduce just after, which I introduce just after. For those who know it's simply related to the Mobius function of the coset. Okay. So this, what I say about the Mobius function is if you have the zeta operator, so just summing what's under a certain, if you, for any node of the coset, any element of the coset, you put a real value, you put you want to sum what's all under an element, then you can inverse this function. And this is what is called the Mobius function. And the way that the functor operates on, like a contravariant Fourier functor operates on distribution is by composition. And this we will see just after. Now that if you want, so what I'm doing now is I'm just trying to explain how I get the message passing algorithm, and then I stop. So to do so, you need to see how f, so your contravariant functor acts on probability distributions. It acts by composition. Now you want to see this as vector spaces, so you can see it as a linear function, so you can dualize, so you do the action on the dual. This you need. And then you want to extend the Mobius functions for functors. And simply what you're doing is when you can move upwards vectors, you move them upwards instead of the face. And so you have a generalization of the Mobius inversion on things like on features that can change for nodes inside of a coset. Okay, so there's missing a CA over here, so this is not good. And yes, I'm cheating a bit because I just didn't put, so we need to solve this optimization problem. Here there's a CA, we need to solve this optimization problem under the constraint that Q is in the limit of F tilde is just F acting on probability distribution. You cannot solve it like this, you solve it for the underlying, let's say, action on vector spaces, and you need to add the constraint that your distribution sums to 1, but this is not difficult. I mean, this is not problematic at all. Okay, and then you get this very nice result, which is that you can characterize the critical points of the beta free energy simply by acting on it by the Mobius inversion and saying that if it's restricted to the limit, it's equals 0. So you get the Mobius inversion of a differential of the free energy is equal to, sum of Lagrange multipliers that allow to account for, that parameterize the dual of lim F tilde. And so these Lagrange multipliers will be the messages, and this gives you a procedure to directly find a message passing algorithm which fixed points are critical points of the free energy. So it's this equation that allows you to define general message passing algorithm for any underlying function. And you can do it like what I said this morning when you have a specification, but it's another way of doing it, but you can do it still. And this is the algorithm, so I don't see the only difference with the literature, which people didn't know how to do, and this I'm sure, with respect to this morning, it's something that I was not sure that people didn't know how to do, but this I'm sure people didn't know how to do, is you change, belief propagation is, this is nothing, just 1, and this is marginalization. And the algorithm, the procedure allows you to say that everything holds, you need to put the adjoint of the map F, given by the functor, and here is simply the push forward, like composition between the Markov kernel and the distribution. And this is a way to do inference on the diagrams in the kernel category of Markov kernels. And I would like to thank you very much for your attention.
Questions? Yes.
So the message passing algorithm for general graphs, like the movie propagation,
Yeah.
like the runtime relates on the complexity of the graph that you start.
Yeah.
Like it's tree weight type stuff.
Yeah. Edges, just the number of edges. The number of edges times the maximum state that you will consider. So basically, it's you take maximum.
Yeah. So if you now allow any diagram path, like any shape, does this method have that same kind of?
Yeah, same
in terms of the tree decomposition of A?
Number of edges in the poset times maximum state space.
Great, thank you.
Welcome.
Why can't the shape be, why does the shape have to be a poset?
Because I don't know how to do the Mobius inversion if it's not a poset. I mean, if you could, then you could generalize.
Yeah, like, because you would look at the category of path, like you take any graph, look at its category of paths, and then as long as you did inclusion, exclusion,
Yeah.
the right way,
Yeah.
that would be the big deal.
Yes, exactly. Yeah.
Kind of a general question, but you mentioned multiple agents at some point. What are you thinking about when you're doing that? Or like, what are the agents? Are they sending like how are they interacting?
I have a concrete example on which this is working, which is basically, so we're interested in structured world model where the structure is so the state space is a homogeneous space. So we're working with this with David Rudroff, which is a computational psychology. So there are some motivations for why the state space could be a homogeneous space. So it means that you have observations and an internal space for representing the environment, which is a homogeneous space. And then what happens is that the way the group acts can change with respect to agents. So the communication is with respect to sending beliefs. It's just a matrix in the end, but then it's non-trivial the way they need to glue together. I mean, the way they have to communicate their beliefs because they're not identical. But then more generally, I mean, any system of communication where you don't have the same world model. And for example, imagine you have more information than another agent, and you can embed. So, okay, a better answer is you do the same thing that people do for like cellular sheaths, like for a sheath neural network, which is that you assume that you have two nodes, have an edge, and you can embed information in the edge. Which is basically you have information, the other one has information, but it's incomplete. But you have a way to communicate it inside of a space. If you take a hierarchy, you can suppose that you have partial information, but you can send it to your boss who has complete information. I mean, like at least more information than both of you.
Okay, let's thank our speaker again.